are filled with over 100 billion neurons which control every single movement, sound, and thought we have. These neurons communicate by sending electrical signals to each other. There are four main parts to a neuron. The dendrites receive signals from other neurons, the cell body processes those signals, the axon sends the signals down the neuron, and the axon terminal passes signals on to the next neuron. Each neuron has an electrical gradient, so there is a difference in electrical charge measured in volts between the inside and outside of the neuron. In its resting state, the inside charge is 70 millivolts less than the outside. This charge is created because of ions inside and outside the neuron. The two main ions around the axon are sodium and potassium, which both have a positive charge. Most of the sodium ions rest outside the neuron, and most of the potassium ions rest inside of the neuron. These positive ions are able to create a negative charge because the ions move in and out of the neuron through many different channels. One very important channel is the sodium-potassium pump. This pump uses ATP, or adenosine triphosphate, to pump out 3 sodium ions for every 2 potassium ions it brings back in. It allows more positive ions to be pushed out than positive ions to be brought in, creating a negative gradient. This pump is always working and uses 20 to 40% of the brain's energy. Also, there are voltage-gated ion channels. Each ion has its own voltage-gated channel, which stays strictly closed until the electrical gradient reaches a certain threshold value. Now, back to the action potential. The charge of the neuron is always changing due to this constant flow of ions and signals coming in from other neurons. However, if a strong enough signal arrives and the gradient reaches a threshold of negative 55 millivolts, an action potential has been triggered. As soon as this threshold is met, the depolarization state begins, so the sodium voltage-gated channels open up and positive sodium rushes inside the neuron. The gradient peaks at about 30 to 40 millivolts, kicking off the repolarization state. The sodium channels close and the potassium channels open. Potassium begins to flood out of the cell, rapidly decreasing the charge. However, the potassium channels stay open longer than the sodium channels did, so the overall charge drops below negative 70 millivolts in this hyperpolarization state. Once the potassium channels close, the neuron enters its refractory period, so there cannot be another action potential during this time. During the refractory period, the sodium-potassium pump works to take out sodium and bring in potassium, restoring the charge. Let's look at the bigger picture of the signal being sent down the axon. When each action potential is sent, a sort of positive charge is being sent down the axon. The refractory period ensures that the signal won't be allowed to travel backwards, meaning that the area the signal just passed has too negative of a charge to trigger another action potential. Once the signal reaches the axon terminal, it is passed on to the dendrites of the next neuron, and this whole process repeats again until the signal reaches its destination. Because of the billions and billions of neurons in the brain, there are over 100 trillion possible action potentials. Mind blown. So the next time you wiggle your fingers or talk to someone or do basically anything really, remember those billions of neurons firing inside of your head.